I don't know how I'm going to do the introduction in less than 3 minutes, but I'm going to be fiercely ruthless with myself as I am with everyone else, as I have been. It's a challenge. Believe me, I'm extremely thrilled that we're able to have Dr. Martin Duncan here to give a talk with us today. Those of you who may have any inkling of the definition of the word cutting edge maybe know something of my perception of what Dr. Martin Duncan is. Because for me, Dr. Martin Duncan is the epitome of cutting-edge astrophysics. I don't know how many times in the last decade his name has been associated with things that are on the cutting, nay, the bleeding edge of what is happening. A decade or so ago, we heard of chaos theory, and he was in the middle of it, especially how chaos theory applied to the orbits of solar system objects. He was there when new ideas were brought out about cometary formation less than a decade ago. He was the one who was there when a great deal came out about what the Kuiper belt was. He was there when predictions were made that Kuiper belt objects might soon be found. And he was there when they were found. And looking over the newspapers of the past 3.5 weeks, I have from the front page of the Kingston Week Standard the article of the discovery of an object that he predicted, which is not a Kuiper belt object, but an object from an area beyond the Kuiper belt. And an article of the same date, Toronto Star, Terence Dickinson, Canadian predicted newfound object. The article is about the Canadian who's going to address you in a minute. Ottawa Citizen, June 5th. Solar system gets bigger by the day. The article that they talked to Martin Duncan about in relation to his prediction coming true about 1996 TL66, which I understand is the largest object discovered in the solar system since the discovery of Pluto and Charon. An object that is over 21%, I think, the size of Jupiter, has an orbit, or sorry, the size of Pluto, has an object that goes in orbit far out, yeah, I mustn't confuse those two planets. An object whose orbit goes far out beyond the orbit of Pluto. I think at its furthest point, possibly 3 times or more the distance out from Pluto. An object whose diameter is something like 500 kilometers, 490, 500 kilometers. His prediction was that these objects would be found, and there may be more of them. And I think it may be a term that he and his group coined that we will be hearing over the next few decades. And I think it's something like SIOs, scattered icy objects. So a decade from now, when the astronomy texts are being written, you will be able to say that you heard the SIOs that will be discussed in those textbooks, first presented, I suppose, at the GA in Kingston. It's an extremely great pleasure for me to introduce Dr. Martin Duncan. Welcome.
Well, that's going to be a tough act to follow. Looking around for this guy. I mean, let's be frank here. There were some interesting developments in the last few years. I've worked with some very good people, but the real credit goes to the observers who found these things. But we are learning more about this region in the outer limits of the solar system. I know people like yourselves will be very interested in. So I'd like to just give you a summary of what we understand so far, what's been happening in the last, especially in the last few months, really, about this idea of a scattered disk. But I always like to remind myself when things are going too well, or you start thinking that you understand nature better than nature herself, of a joke somebody sent me, an email message I got a few months ago, and it's apparently a transcript of a real radio conversation at sea. And operator number 1 on the radio says that, I'm making up some names, this is the USS Alabama. We request you change course 15 degrees southward to avoid collision. Over. So the operator number 2 says, we suggest you change course 15 degrees northward to avoid collision. Over. And operator number 1 says, this is the commanding officer of the U.S. warship Alabama. Strongly suggest you change course 15 degrees southward immediately. Over. Operator number 2 says, this is a lighthouse. Your call. The reason I bring that one up is I like to think about that because often as a theorist, we have this mental image. You build up a mental image of what the solar system is supposed to be doing. This is how the outer solar system is supposed to behave. And we're always surprised. Nature always has tricks up her sleeve. And it's especially true, as you know, in planetary science, when you start investigating, you fly by a moon and suddenly it looks nothing like what was predicted. So I think there are more surprises in store for us, especially in other planetary systems, but even in our own, in the outer limits. We really don't understand exactly what's going on out there. So let me try and give you an understanding of how the ideas have developed about this region of the solar system. And I will not cover all of these topics. This is the transparency I used for recent talk at a professional society. But I'll give you some idea of what is this thing, this Kuiper belt? What is this scattered belt, or these scattered icy objects? How do they all fit in to our understanding of how the solar system formed, which is what we're all trying to get at. And let me remind you about the standard picture of how the solar system formed is that, again, no, I'm sorry, it's not great in this lighting, but this is a picture, if I can find here, an artist's conception, obviously, of what we think how the solar system might have formed. And the key part about this is, as I think you all know, it's believed that the sun formed out of a cloud of collapsing gas and dust. And because it had a small amount of rotation, as it collapsed and started to contract, it spun faster and flattened out into a disk. And in that disk, objects, such as these objects shown here, formed. These are so-called planetesimals. These, in fact, are fairly large planetesimals. Before this state, up in here, there were probably trillions of these things, all orbiting around the sun, coagulated dust grains, and in the outer parts of the solar system, they would have been coated with ices. And as they grew to kilometer-sized objects, we believe that they would look like current-day comets. And so this is the picture then of how the solar system formed. And in the end, we end up with a bunch of large bodies. And the question is, what happened to all the little ones? And it's related to this notion, thanks to Terry Dickinson, this particular picture, of the Kuiper belt. Here's the sun. Way down on the scale, down in there, is where the terrestrial planets are. But I'll be talking mostly about Jupiter, Saturn, Uranus, Neptune, and then finally Pluto, orbiting on this weird kind of unusual orbit out there. Pluto was always an outlier, an unusual object in the solar system. We now think it fits very naturally into this whole notion of many hundreds of millions or billions of objects orbiting out beyond Neptune. And if we were to look on this edge on, the critical factor about this Kuiper belt, from a theoretical point of view, is that it's a flattened disk. So seen edge on, the red things are the giant planets. Pluto, somewhat inclined, is orbiting amongst myriad other objects, which are only now being found. So that's the basic idea. Let me remind you about comets. Most of you here know the distinction between so-called long-period and short-period comets, but let me remind you of that with an illustration. Here's the orbit of a comet that all of you have probably known and loved in the last couple of years. But the main thing to note about it is it comes streaking in from very great distances and goes back out again on a highly inclined orbit. Here it is shown edge on and to the solar system. So these objects come from great distances, and typically, as most of you know, they come from distances which are on the order of about a tenth of the distance to nearby stars. So there's a big cloud of objects called the Oort cloud of cometary material. Trillions of comets orbiting out there. If I have time towards the end, I'll talk a little bit about how they got there. They were probably scattered out. In short, they're scattered out by the planets as they were forming. So there's one smoking gun for the origin of the solar system. But there's another smoking gun that tells us something about what was out there even before it was found. And those objects are the so-called short-period comets. And here we have, now on a smaller scale, Mars, Earth, and blue. Here's an object that's going around us, and this is typical of the short-period comets. They have apocenters near Jupiter and pericenters near to the sun where they can be seen. If they had pericenters out at 3 or 4 AU, they become much harder to discover. They don't have the nice tail that distinguishes a comet when it comes close to the sun, so they're hard to find. However, we know of on the order of 100, there are probably a few hundred such objects orbiting around close to the sun. But big Jupiter here doesn't like small comets orbiting in its vicinity. It has such a strong gravitational effect, it tends to kick them out. So there must be some source of replenishment for these objects. And people long thought it was the Oort cloud, that maybe comets came like Hyakutake came in, and a small fraction of them would come close enough to Jupiter or one of the giant planets to be drawn down to a much more tightly bound orbit. And that was, it was thought, the way that you might form these objects, short-period comets. There is, in fact, a long history to this whole idea of the Kuiper belt, and this, I won't go into all the details here, but we welcome any questions that people might have. But there's a long history behind this, and if there's anything I've learned about studying things in the solar system is that there are no new ideas. Everybody's thought of a great idea that you suddenly thought you had. You look in the literature and people have had just about every possible idea about origins in the solar system. The basic idea about this Kuiper belt, historically goes back at least as far as Edgeworth and Kuiper, who basically said, why should the solar system suddenly stop at the planet Neptune? After all, if you take all the mass in the heavier elements in the planets, just disregard even the hydrogen and helium, but take the cores of the giant planets and smear it out. If you extended that distribution that you find beyond 30 AU, you would end up with a prediction of that there should be tens of Earth masses worth of material beyond the planet Neptune. And yet, at this stage, nothing at all had been found, except the planet Pluto. Now, the history then goes on to Fernandez in 1980. So we weren't the first to talk about this as being the source of the short-period comets. Julio Fernandez from Uruguay, in fact, suggested that the short-period comets, the ones, as I said, with short periods, less than 200 years, might come from this region. And they even suggested something which is also prescient, and that is that if you were forming giant planets, if indeed the planets formed by the coagulation of millions or hundreds of millions of these icy bodies into larger and larger things until you form planets, then not every object would be incorporated into the giant planets. Some of them would come close to a planet, but would be gravitationally perturbed into a very different orbit. And so they, even in 1983, were talking about the possibility of a scattered disk of objects. Things which encountered Neptune billions of years ago, but which still might be hanging around in the outer parts of the solar system. And their exact mechanism, I don't think works, but the basic idea was theirs. Then we made some contributions suggesting that the main reason that you might think a belt is out there is that when you look at objects that are captured from a spherical distribution of objects, you started with comets coming from all different directions, and that's characteristic of the long period comets. There are some small signatures of the galactic tidal field, as we'll hear later tonight, but in general, they come from random directions. And we found in our computer simulations that if you started with a population, like Hyakutake and other ones, from all random directions, and followed them on the computer until they came close enough to the sun to produce that tail, that the distribution would retain many of the properties of that random spherical distribution. In other words, it wouldn't look nearly as flattened as the actual short-period comets are. And in fact, again, I'll show a few plots like this, but don't worry about the details. Technically, I think you can see visually that if you start with, these are the real comets, this is their average distance from the sun, this is their inclination, unfortunately the radians here, but these are all down at 10 or 20 or 30 degrees. Inclined meaning that their orbits are tipped a little bit to the plane of the solar system. Unlike the planets, which by and large go round in nearly coplanar, nearly circular orbits, these objects are fairly eccentric, but more importantly, they're somewhat inclined, but not hugely inclined. And if they came from the Oort cloud, they would look like this and look nothing like that, whereas at least this population, what's sometimes called the Jupiter family, those with periods less than 20 years, the bulk of them here look very much like this population. So that was our argument in 1988 about the existence of this belt of materials. And there were other arguments too, even before the first discovery of an object, that go back to Mike Torbit in 1989. Again, somewhat prescient chaos, and he talked about scattered disks. Again, I think the details of the mechanism weren't quite right, but he certainly had some of the right ideas. And then a student here, Brett Gladman at Queen's, showed that if you started with objects between the giant planets, they would be scattered out to large distances by the slow buildup of the gentle nudgings of the planets by a process which is known as chaos. Let me digress for just a moment and show you an example of a chaotic system. Some of you may know the definition of chaos is not necessarily that the system goes completely bonkers, but rather that there's an extreme sensitivity to initial conditions. So what's happening in our solar system, as we've only begun to realize in the last 10 or 15 years, due to the work of Laskar and Wisdom and others, is that our solar system is indeed chaotic and hence unpredictable in a detailed sense. It's not that the planets are about to fly off into space, but that it is true after, say, 100 million years into the future or past, we won't know which side of the sun the Earth will be on. We cannot predict that. And the reason we can't is related to this notion of chaos, which I can demonstrate. Since I can't bring the solar system in, I'll bring in a simple example of a double pendulum. This is a system, a simple physical system, which has a rod here, you're welcome to come up and look later if you like, and another rod suspended from the bottom here. And this one can go freely through the other one. But this is a simple system because physically it has 2 degrees of freedom. 2 angles are enough to specify the position of the object at any given time. And if I start the system off from an orbit that looks fairly small amplitude, then it swings in a kind of regular, predictable way. And you could believe that this system, you could write down some equations and predict its behavior a long time into the future. And that is true for this particular set of initial conditions. But I can always start the system off, same system, same physics, same equations, but I can start the system off in a different initial state. And if I start it off in a state like this, then I get all kinds of unpredictable behavior. You can see how, you can imagine how difficult it will be to predict how this system is going to behave in detail. And if I started with 2 systems very close to one another, they would diverge exponentially with time. And the main source of it is when the pendulum the bottom one gets near to its tip here, the slightest nudge either way can make it go one way or the other. And the slightest change in initial conditions will make it go the other. So that's a chaotic system, and our solar system is like that. And it means that the orbits of objects, including the planets, are chaotic. And although it doesn't predict that the solar system is about to fly into space, as I said, it does suggest that maybe earlier on we had more planets, and that some of those have been ejected, and the system has settled down into a state of marginal stability. And there is a small but finite chance that, for example, Mercury will be thrown off into space, and then Pluto will become unstable. Although Pluto looks fairly stable, more stable than Mercury, actually. But it's all chaotic, and that has consequences for what I'm going to be talking about. Let me not dwell too long on some of this, but let me just remind you that the first planetesimal was found in 1992. This is the first member of the Kuiper belt, and this was something that we fully expected to find, I must say. This, when it was first found, we said, this is great, problem solved. Here's an object going in orbit beyond the planet Neptune at a distance of about 42 AU. Neptune's at 30, this thing's at about 40. It was in a nearly circular orbit, it kind of looked like a disk, and it looked a lot like what we had been thinking we would find. So this looked very promising. But nature has some tricks up her sleeve, and first of all, let me point out that most of the objects that have been found from the ground so far are very large objects. This is not even complete. There are now something like 30 or so objects found, just showing a fraction here known as about 1995. But they also, up till now, up until the last few months, they have fit in a certain category. They had radii which were on the order of, say, 40 to 120 kilometers, and their range was somewhere out here from 30, this is where Neptune would be, they orbit out in this region. And they have fairly low inclinations, with the exception of this one up here, a few degrees. So that looked like a belt. But in fact, the distribution of objects in the belt is not what I at least expected. And again, let me not, so this is a technical transparency a little bit, but let me, if I can get it the right way up, here we go, all possible orientations. Here's this is a busy slide, but let me just point out something very important about it. This is a plot of computer simulations of what you might expect to find out in the Kuiper belt. And if you had objects which were of low eccentricity, nearly circular orbits, and you put down a bunch of objects out there on 4 billion years, you would expect to find a lot of objects between 36 and 40 AU on nearly circular orbits, and some out here. But what in fact is found are these green dots. And what you discover is that these objects are like Pluto. That many of the objects in the inner parts of the Kuiper belt are on orbits which are in what's called a mean motion resonance with Neptune. That is, for example, in here, this is Pluto itself, by the way, on this plot. It has high eccentricity. In fact, it crosses the orbit of Neptune. But it's stable because it is locked into what's known as a mean motion resonance, in which it makes 2 orbits for every 3 of Neptune, which means the whole system comes back together again after just a small number of periods. And what you end up finding is, for example, and this was known even before the Kuiper belt was discovered, what was known was that, for example, Pluto followed a peculiar kind of orbit which kept it away from Neptune. What's plotted here is plotted in a frame which is rotating with Neptune. Imagine getting on a turning wheel which rotates at the same average speed as Neptune does. And then look at the orbit of Pluto. What you find is it traces out a path that looks like this. It goes round, it does a loop, comes over here, does a loop-de-loop, goes round, and it oscillates back and forth on a much longer time scale. But you'll notice here's Neptune, and Pluto never comes very close to Neptune. Hence, it never has a chance to be strongly scattered by Neptune, and this is why Pluto's been around for billions of years. And this is probably why at least some fraction of the objects in this region, if I could put this back up again, many of these objects right in here lie in the yellow region of this diagram. These are objects which can avoid encountering Neptune on a 4 billion year time scale. But you'll notice there's some color in here which tells us from the computer that you can diffuse out of that region. You can actually spread out from there by the chaotic effects of the giant planets. So you can trap things in the Kuiper belt, but they will slowly leak away. So what we have is a leaky reservoir which is capable of slowly trickling things in. It's like a big bathtub with a pinhole in it. Things are slowly leaking out, and they're encountering Neptune on billion-year timescales. So we wanted to follow these objects on the computer. We wanted to see, and of course that's where the short-period comets are coming from. We thought they're leaking out of nearly circular orbits, low eccentricity orbits, nearly coplanar orbits, beyond Neptune, and they're leaking out because of the effects of chaos. This kind of motion here eventually leads to some fraction leaking out on billion-year timescales. And when they leak out, they encounter the planet Neptune. When they encounter the planet Neptune, they begin a migration. And they migrate both inwards and outwards. And I'm going to cut this short so we'll have some time for questions at the end. But basically, we have an armada of material which is on its way from Neptune down to where the Earth is, where they become comets. And the basic mechanism we found from computer simulations was in fact first suggested on other grounds by Everhard in the 70s. So again, lots of stuff precedes us, but what we found by more accurate calculations is that when an object encounters Neptune, it gets passed downward. Some of them, at least, move inward. This is Uranus here. Then passed inward to where Saturn is. So you go from an apocenter near Neptune, or apo beyond Neptune and Peri, the closest approach near Neptune, to one where the Peri is near Uranus and apo is near Neptune, to one where the apo is near Uranus, Peri near Saturn, etc. You get passed on. Now, of course, not all objects follow this, and it's not a one-way street. It's rather like the usual argument about a drunk, who's standing near a lamppost, takes a step, falls down, doesn't know which way he is, takes another step. So sometimes he moves one way, sometimes another. This is what's called a random walk in physics. And things diffuse outwards and inwards. And some small fraction of them come down, where they can become short-period comets. And we, in fact, can now predict the distribution of such objects. And there are indeed objects like Chiron and several other objects that have been found in the last few years, which are intermediate between objects in the Kuiper belt and short-period comets. And we would predict, in fact, that there should be about 10 million or so of those objects, ranging in size from kilometer-sized objects up to the very large 100-meter-sized objects. And in fact, I won't show you, but perhaps you'll take my word for it, that again, we get very good agreement between the population of short-period comets from our simulations and the real objects that we find. Furthermore, we in fact would predict that, it's quite obvious that if you have lots of objects orbiting in the solar system, some of them are going to run into Jupiter, just like Shoemaker leaving 9 that you've all been hearing lots about. And this, from our simulation, should happen once every 400 years to Jupiter. Once every 10 to 100 million years for the Earth. Comet-sized objects striking a planet. And Jupiter is a big target, strong gravitational focusing, and it's a big target. So this happens quite regularly. So we thought everything was hunky-dory there. The picture seemed to be pretty nice until we looked at what was happening to our objects encountering Neptune. And so again, to backtrack, what we've done so far is we've talked about computer simulations taking objects in nearly circular orbits beyond Neptune. By integrating them for billions of years, we've discovered that a small fraction of them are very unstable and will encounter Neptune very early on, and that a small trickling could be coming from objects in the Kuiper belt, this region beyond Neptune. Stable or quasi-stable, low eccentricity orbits, low inclination orbits. So we had followed these objects on the computer. Once they encountered Neptune, once they came close to Neptune, we followed them up to then for 1 billion years. And we were kind of puzzled because what we found was that instead, as we expected, what we expected was that most of them would have been long gone. If you had an encounter with Neptune 4 billion years ago, what we found is that the average lifetime of an object that encounters Neptune towards being scattered in or being scattered out towards the Oort cloud, that time scale for the median was about 50 million years, which is 1/1000th of the age of the solar system. Very short. So we thought, well, there should be nothing really left of this scattered population of objects. But what we found on the computer was that if you started with a fraction, let's normalize it to the initial number. Suppose you started with 1 billion objects or something initially, encountering Neptune. We're not talking about things in the belt, we're talking about things that have had their first close passage with Neptune. Let's follow them on the computer and ask, how long will they survive? Well, what you find is that as you go on in time, and this is billions of years now, and this is the age of the solar system, is that there is a very slow decay towards the end here, although it's very steep in here. You end up with something like 4 or 5% being left still scattered around in this debris disk. This bit of scattered icy objects, which have encountered Neptune once, but remain in orbits beyond Neptune, but very unstable, wandering around, scattering, but remaining out there. And what we found is that after 4 billion years, there was still about 1% of the objects left. And this was very surprising, and we didn't know why it was happening at first, to be quite honest. But what we discovered was that what was happening was that objects were scattering off Neptune, and then this is, again, a little technical of a plot, but maybe I can just try and explain it in words. This is the distance from the sun, and this is time in billions of years. And this is one particular object that we're following. And the object starts out here with an encounter with Neptune. This is the distance of Neptune here, and this is further out. And so what happens is, very initially, all of these objects start by encountering Neptune. They come within, technically, what's called the Hill sphere, which means that for a while, they're more strongly affected by Neptune than by the sun. So they're definitely scattered into a completely different orbit. They may have leaked out of the belt early on, or come from some other region in the outer solar system 4 billion years ago, but once they encounter Neptune, they wander around out there. And this one, as you can see, goes out to 80 AU, drops down to 60 AU, and then it lands in this location here, where it seems to stick for a while. And the crucial part about this getting stuck is that its perihelion distance, its closest approach to the sun, gets lifted further away from Neptune. And this explains the survivability of these objects. What we find in the simulations is that objects that have once encountered Neptune, a small fraction of them, a few percent, will find themselves trapped near these mean motion resonances. This 4 to 7 means that it's near a resonance where it makes 4 orbits for every 7 of Neptune. And this is due to the stickiness of these regions is due to chaos. But the important consequence is that the perihelion is lifted up to this region out at about 35 AU. Let's remember that number, because a lot of them get stuck right around 35 plus or minus 3 AU, and they get out to distances which are on the order of 50, 100, even 150 AU, and wander around out here, and then you'll notice what happens at the end here. The perihelion drops back down, falls out of the sticky resonance, and once this happens, this object then begins to migrate inward to become a short period comet, or it may, if it encounters Jupiter, get kicked out of the system entirely. So what we've got is a new population of objects, and if you look at their distribution, what you find is the following properties. And again, this is a bit technical, but let me just explain. The bottom one is the crucial point, is that if you plot the distribution of these objects in space, you expect them to have low eccentricity within 50 AU of the Sun. But as you go out to distances on the order of 70 or up to 100 AU, you expect these two triangles here indicate the range of eccentricities we find in our computer simulations. The reason that they're so tightly bounded in here, that you find objects only in this region, is because out here, when you're out at 120 AU, this kind of eccentricity, this elongation, will bring you to about 36 AU. So this is an object that is still being affected by Neptune, but is slowly diffusing on billion-year timescales. So we predict a distribution of objects that have perihelia near Neptune, and hence have eccentricities that lie along this line here. And also, they should have inclinations which are a bit higher than the typical disk objects. Their inclinations should be up around 30 degrees or 40 degrees. More tipped up because they've been scattered around. So that was where this all stood about a year ago. And then we saw the IAU telegram, which indicated that Jane Liu and her team, Jewett and others, observers, had indeed found, as Leo said earlier, the largest object so far in the Kuiper belt, although they've been sitting on another one. Our secret suspicion is they've been sitting on a brighter one because they wanted to write this paper about this being the brightest member so far found. There's another object in the Kuiper belt, which is even slightly, it's a bit of a canard, but anyway, a bit brighter than just announced, that's in the classical Kuiper belt, but it's even bigger than this one. But the remarkable thing about this one is not so much the orbit it's on, because as you just saw, these are the kind of orbits that you were expecting, but the size of the object. The first one found has been found in an orbit that looks like this. It's going around here's the Sun down here. Here are Jupiter, Saturn, Uranus, and Neptune. All this busy stuff here are the other Kuiper belt objects discovered from the ground. These are all largish objects. The only things you can find from the ground are on the order of 50 to a few hundred kilometers. The things you can find from space, such as the Hubble Space Telescope, are things more like Halley-sized objects. Now I'm digressing for a moment because I realized I forgot to mention the Hubble observations. They are controversial. We have a team led by Anita Cochran and Hal Levison, Alan Stern and myself, have argued from statistical images taken with the Hubble Space Telescope that there are many comet-sized objects out there. There is some dispute about that, and I think the answer to that is to wait. In August 15th through 20th, Hal and Anita have been given another 50 hours of Hubble Space Telescope time to probe even deeper in this region. And so either these results will be confirmed, or if there was something wrong with the statistical analysis, they'll be refuted. But we'll know within 6 months whether or not there really are lots of comet-sized objects out there. There have got to be, in my opinion, comet-sized objects out there. I believe. I believe. So, whether or not those objects are in the classical Kuiper belt, that is, in orbits which have remained unperturbed, have not encountered Neptune, or whether they lie in the scatter disk, is actually now a very interesting question. Because now that we've discovered this object here, 1996 TL66, on this very eccentric orbit, it fits perfectly with the idea of a scattered disk. Now this object is very large, and the surveys that discovered it have only looked at 1/1000th of the sky. So Liu and Jewett argue, I think obviously quite correctly, that it would be very improbable that this first object found would be the only one he found. The chances are less than 1/1000 that they would have found only this thing. So there must be many of these objects out there. And they do a very crude estimate, which everyone would agree is very crude, because we have only one object. It's hard to do statistics on one object. But if you do some statistics and estimate what's out there, you might find that there's on the order of an Earth mass or so worth of material in fairly large objects out here, and it would only take a tiny fraction of those objects in mass. It would still require on the order of 1 billion comets to be out there, but it would not be much of an extrapolation from this one object to believe that there's a whole population of scattered objects out there, which also could be the source of the short period comets. So the nice thing about the scatter disk as the source of short period comets, so what I'm arguing now is it's conceivable, as I said, I had a mental image anyway, that this Kuiper belt, this region of objects which formed beyond Neptune, they formed small bodies up to a few hundred kilometers across, but those objects never partook in the dance which formed the giant planets, never partook in the merging process that formed the giant planets. They were just out there and never formed anything very big. That was the classical, if you can call it that, classical Kuiper belt. Now, as a result of this discovery and the simulations, there's the possibility that what's really happening is, although there are a few objects out there in the Kuiper belt, maybe most of the smaller objects lie in the scattered disk of planetesimals. Now, people would not have thought this was likely to have happened because people thought that anything which was scattered by Neptune during the process of its formation 4 billion years ago would have by now been kicked out of the solar system, moved inward or outward, and finally been gone. But now we have the possibility that this, because we found from the simulations that 1% of these objects could be left. If you say that 1% are left now, and there's something on the order of an Earth mass worth of material there, then you only need something on the order of tens of Earth masses to encounter Neptune early on. Now you may say, that seems unlikely. How can you possibly have that much stuff out there? But Neptune and Uranus themselves have masses on the order of 10 or 15 Earth masses. The process of planet formation certainly was not 100% efficient. Furthermore, we have evidence that the Kuiper belt itself has been stirred up. There are regions in the Kuiper belt where there could be stable orbits, those low eccentricity orbits between 35 and 40 AU that I mentioned early on. Those orbits should be populated. They could have, if things formed there after the planet settled down, those objects should be there now, and they're not. The Kuiper belt shows every evidence of them having been stirred up to a great extent by the process of planet formation. And one of the best mechanisms for forming Pluto and those other objects like it is that Uranus and Neptune, as they were forming, were scattering so much debris that they scattered a lot of it, as it happens from simulations again. Most of it would move inward, and if they scattered stuff inward, they would have moved out. So Fernandez and Imp argued that Uranus and Neptune moved out, and they'd sweep up a few things into the 2 to 3 resonance. So we have evidence that the outer solar system, the process of planet formation, was extremely chaotic. The planets were moving around. We know from the fact that there are planets with tipped over axes. Even Jupiter must have been hit, rather Saturn was probably hit by a Uranus-sized object to explain its tilt. And Uranus was probably hit by an Earth-sized object. So there was a lot of stuff out there scattering around. And so now the picture is becoming, in some senses, more interesting. Perhaps what we're getting are, what we're seeing in this scattered population out there is both the source of the short period comets. We're also seeing a reservoir out there. And then you can ask yourself, what happens to those objects which have scattered off Neptune and have moved outwards rather than inwards? Remember I said it was like a diffusion process, things wander inwards and outwards. Well, if they can move in both directions, then what happens to the ones that come and get scattered by Neptune? They move to greater and greater distances. But what happens to those objects is they form the Oort cloud, and as objects which began in the region where the giant planets were forming, as they were scattered outward, they would be scattered outward in the plane of the solar system. And that's this plane here. The reason that I'm showing it at such a weird angle, this is the plane of the planets here, the orbital plane. The reason it's so weird is that it turns out that our solar system is inclined at 60 degrees to the plane of our galaxy. So as objects move further and further out, they get gravitationally perturbed out here by passing stars, which on this scale are going by over here, and the tidal field. And they get randomized, they get their perihelia lifted away, and they form the Oort cloud. And so some of the stuff that's been scattered by Neptune almost certainly has ended up in this Oort cloud. So just to finish up, let me finish with one really speculative notion. Is in the old days, people said that the Oort cloud formed a short period comets, and that's all you needed. Then people argued, well, that doesn't work, so we need another reservoir. We need a Kuiper belt to explain the short period comets. Well, let me now argue that maybe you need the Kuiper belt to form the Oort cloud. That is to say, if you had a lot of stuff that was forming out in the Uranus-Neptune region, especially beyond Neptune, then that stuff is very efficiently scattered by Neptune outwards and has lots of time to end up in the Oort cloud. Whereas the stuff that's scattered inward, down to where Jupiter and Saturn lie, are scattered out of the solar system and never end up in the Oort cloud. So since we found that 1% of the Kuiper belt objects encountering Neptune early on survive for the age of the solar system, we only need a scattered disk, which is an order of magnitude or two less than a Kuiper belt we were talking about earlier, and you can supply all the Jupiter family comets, and these two guys probably are the first two members to be discovered. There's another one I didn't mention, which also we think looks like a scattered disk member. This is the most obvious one. And then finally, you could have formed this in many ways, this Oort cloud, but ironically, a massive Kuiper belt is an efficient source for the Oort cloud itself. So our pictures are changing in real time. Thank you very much.
Time for one question. Very sorry. Alan.
If I understood correctly, you're saying the observed population in the 2 to 3 resonance is not a primordial population. It's a population that was pushed there by the upward migration of Uranus and Neptune.
That is one model. There's a model by Renu Malhotra in that by pushed, I don't mean scattered there in the sense of coming close to Neptune. But it turns out that if Uranus and Neptune scatter material inward, they will migrate outward. And the gravitational effect is to trap objects still further out and push them into the 2 to 3 and keep them there. So they may have been trapped into that resonance by the outward slow migration of Uranus and Neptune. That's the model of Renu Malhotra. There's some problems with that model, but it's one plausible way for producing Pluto and other objects like that. But they're not scattered in the same sense I was referring to today by a close encounter with Neptune, but rather by the effects of the mean motion resonance movement of the compass.
So you say no primordial Kuiper belt left, it's all in the Oort cloud are gone. Instead we have the scattered disk.
We're saying that there are some residual population of objects still in the Kuiper belt. There may not be enough comets in the current Kuiper belt to explain the origin of the Jupiter family comets, but there certainly should be enough in the scattered disk to provide all the Jupiter family comets. So there definitely are still some objects in the Kuiper belt, in the classical Kuiper belt, that have been unaffected by close encounters with Neptune. But that population may be rather small compared to the population in the scattered disk. Surprisingly.
I apologize to about 3,000 people here who all want to ask questions of Dr. Duncan. Incredibly interesting, informative, cutting-edge presentation about what's going on in Kuiper belt, scattered object, and so on. Let me say we deeply appreciate his coming, and as a small token of that, we give you this gift, and thank you again very much.
Thank you very much. I'm sorry there's not enough time for questions, but I'll be glad to talk later at the banquet.
Thank you very much. Please see him at the banquet. He's going to be busy at the banquet, let me tell you.